Thank you, everyone. I am Giri Chakkapalli from NVIDIA Infrastructure Division in the CTO office. By the way, I am really rooting for this ecosystem to take root and flourish. From Jensen on, we have an internal alignment to work with and hopefully play with the interfaces as they converge and formalize in the next year or so. So in the presentation, I'll talk about briefly what's the HPC and machine learning algorithms applications provide the constraints to chiplets and interfaces, which is the main focus of NVIDIA's business. So first, I'll briefly talk about where the ML algorithms are going. As you know, there is a phase shift. If you look at the graph on the right side, from 2012 on or so, they're on an exponential curve for the requirement of the compute resources for machine learning compared to previously. And in like GPT-3, then the number of weights, the machine times blowing up exponentially. This cannot continue in the long run. The main reason is actually is due to use of dense algorithms. Dense algorithms come from a neuron in every layer of an artificial neural network, contribute weights to every neuron in the next layer, resulting in a dense matrix. And dense matrix algorithms are extremely compute intensive. And at this point, to train an advanced model, it costs several million and takes the power of a small town. And this cannot continue at this rate. So researchers are already looking at various ways to optimize these algorithms. One of the key innovations coming in this space is sparsity. In fact, I believe the lottery ticket hypothesis comes from Facebook research team, FAIR. And there is graph neural networks that's becoming popular. Google recently, Jeff Dean published, actually last week, this Google Pathways, again, has this highly irregular, sparse algorithms. The inference is already sparse. So basically, the machine learning algorithms, as we go forward, will become sparse. They cannot fit on a single GPU or accelerator, not even a single node. So they have to be distributed, and they have to employ multiple algorithms to scale to the exploit the available parallelism. On the HPC side, HPC algorithms are already sparse, irregular, and distributed, and they exploit multi-level parallelism through distributed MPI and shared memory SMP. But the one difference is traditional HPC algorithms are always using full 64-bit high precision, double precision. They're moving to more starting to exploit mixed precision algorithms. So the second revolutionary changes that's coming in HPC is they lock, stock, and barrel start using machine learning to accelerate the HPC algorithms. So basically what I want to say is that both HPC and machine learning are converging towards each other, and the resulting algorithms are becoming extremely sparse. They are much more data movement bound rather than compute bound. So it's not the switching transistors, but it's moving data. That's extremely critical. And this has enormous implications on how we break up the chips into chiplets and the interfaces, protocols, and latencies. So my ask for this team is the co-design of hardware, software, and algorithms are extremely critical. The chiplet team should have somebody who understands algorithms to drive towards the right decisions of where things are broken up into pieces and what the interfaces are. And here is a somewhat busy slide, obligatory Moore's law slide. Originally, Moore's law meant actually three things. Every transistor density doubles, power stays same, even though now we are computing double this at double the performance, and the cost stays same. This is no longer true. Both the cost is no longer staying same, and power is not staying same. Power is keep increasing. So if you look at the insert in the top left corner, the per transistor cost is actually after 14 nanometer, I believe, actually start increasing due to litho and other reasons. The other interesting thing is this is scaling, transistor scaling continue to happen, but it actually creates a very distorted scaling. In other words, the switching transistors are scaling, but the wires are not scaling. And the picojoules per bit to actually do a fuse multiply add is actually scaling, but moving data from even within the chip, across the chip, across various levels of memory hierarchy is not scaling as good as the transistor density. So going forward, the beachfront bandwidth becomes extremely critical. In fact, the two criteria, if one thing that comes out of this talk that's critical is that bandwidth for HPC and machine learning applications I'm talking about, the millimeter beachfront bandwidth and power power and energy are the two critical concerns that has to be taken into account when designing chiplets. And typically in HPC, these are measured using bytes to flops ratio. So the 3 bytes to flops ratios that are critical are bytes to flops ratio of the on-die fabric, NoC, network on chip, bytes to flop ratio of memory bandwidth to supply the data, and bytes to flops ratio of the interconnect bandwidth, since the applications of our algorithms are becoming distributed across the lot more than a single GPU or accelerator or a single node for that matter. So here is some of the example bytes to flops ratios or values for the recent 2 generations of NVIDIA GPUs. As we grew, like for example, floating point operations, let's say bfloat 16 here, from 125 teraflops in Volta generation V100 to 625, which is 4x plus, almost 5x. The on-die fabric bandwidth only marginally doubled, and memory bandwidth is a little over double. I/O bandwidth is doubled. So in other words, we can keep squeezing floating point performance, but it's increasingly hard to keep feeding these chips or chiplets. As I said, this will create the beachfront congestion. Like for example, the on-die fabric NoC bandwidth is several terabytes per second on the existing chips. So when we break it into multiple chiplets, we can't reduce that by order of magnitude or 2 orders of magnitude. Then they no longer function as a unified chip. These ratios need to be taken into account when we break the interfaces, what we want to implement when we break down the die into chiplets. Of the existing high performance protocols or interfaces, we are looking at and watching OpenHBI, Bow interposer, and AIB2 as the most promising from HPC and machine learning perspective. So call to action is hopefully interoperable or convergence of these 3 protocols, and laser focus on picojoules per bit, because in addition to switching cost, energy cost, power cost, the IOs start costing a lot more, and gigabytes per second per millimeter shoreline bandwidth. And the other ask is to create distributed systems at reasonable efficiency and latencies. It's critical to explore photonic chiplets, maybe initially probably right next to the package, but eventually it has to be in the package with a low latency, low power interface between the photonic chiplet and the compute ASIC. So the conclusions are essentially ML and HPC workloads are converging fast, and they're becoming sparse, irregular, and they're much more data movement bound rather than floating point flops bound. And these are highly distributed across the whole system rather than in one GPU. This causes extreme congestion on the interfaces, puts pressure on the beachfront. The focus on chiplet design and interface design for HPC and machine learning should keep energy as a critical criteria and bandwidth per millimeter as the another criteria. Thank you.